Okay, last section we need to deal with, or the last chapter is chapter 10, particular 10.1. Okay, so this is about sequences and summation notation. Okay, so we're all kind of familiar with sequences. If you've taken like maybe IQ tests online, you know, what's the next number in the sequence kind of question. Maybe the sequence is something like, for example, 1, 3, 5, and then you have to pick what's the next number, right? So the next number, obviously 7. They're just going up by 2 every time. And we can go on and give a general formula to predict basically what this nth value is going to be. Right? Anyways, the technical definition of a sequence is a function whose domain is a set of positive integers. Okay? So where before we may have had a line representing the function f of x equals 2x minus 1, now we have a bunch of dots where the integers are, right? So it's a function whose domain is a set of positive integers, so we only have points at 1, 2, 3, 4, etc. Okay, so at 1, this would be 1. At 2, this thing would be 3, and so on. Okay. So instead of having a solid line, you're just going to have a bunch of little dots. And instead of this notation, this f of x, will have this a sub n notation, which will equal 2n minus 1. Okay. But they're kind of basically the same idea. It's just in general, whenever they introduce it, it's going to look more like this than the old function notation that we've been using in this class. So anyways, let's dissect this thing and talk about its pieces here. So this is the first term. It's the second term, obviously. And we can give these guys little names. Instead of saying f of 1 and f of 2, we're going to say a sub 1 and a sub 2. It's basically the same sort of deal. I mean, you could also write it, if you're so inclined, as a of 1. Okay, but we usually won't use this notation. You could also write this as a of 2. We're not going to use that notation. So little a instead of little f. Finally, this guy right here is the nth term, a sub n. Okay, this is basically just the formula then for generating any sequence value. Okay, so as I've been saying, these things are just like functions. So if you needed to figure out what a of a sub, let's see, this is 1, 2, 3, 4. You want a sub 5 maybe, and we can't, for some reason, figure out what that is. We could think of this a sub 5 as a function a of 5, where you're plopping 5 into this formula here. Okay? So what is a of 5? Well, that'll be 2 times 5 minus 1, which is 10 minus 1, which is, of course, 9. And that is what we would suspect to be the next term in the sequence. We wouldn't even have to think about it. We would just say, oh, the next guy is 9. Right? But if maybe, for instance, somebody wanted to know the 20th term of the sequence, that'd be a different story, right? Because you'd have to sit there and kind of enumerate every single one of them. But with this formula, you can just plug in 20 and you'll know the answer. Okay, so we're going to get a bunch of little equations like that that will help us figure out maybe an unknown sequence value, or on the other hand, also adding all these things together. We'll want formulas to have those on our hands. So anyways, 2 times 20 is 40, minus 1 is 39. So the 20th term in this sequence would be 39. Okay. As far as the book goes, in the beginning, they're just going to want you to write out the terms of the sequence given a formula. Okay. So here's problem 6. So they give you their nth term formula is negative 1/3 to the n, and they want you to write out the first 4 terms. So they want a sub 1, a sub 2, a sub 3. And I know I'm going off the page. I'll pick it up here first. One second. Hold on. Taking my medicine this morning. Okay, so anyhow, a sub 1, all you're doing is plugging in 1 for n. It's just like our old function notation. So negative 1 to the 1 first power just gives you back negative 1/3. Negative 1/3 squared, a negative to an even power is positive, and then 1/3 times 1/3 is 1/9. Negative 1/3 cubed, negative to an odd power is negative, and 1/3 times 1/3 times 1/3, that'll be 1/27. Finally, negative 1/3 to the 4th, it'll be positive this time, and 1/81. You're going to encounter some things that you hadn't seen before in the world of functions. Okay, for instance, this number 12, a sub n equals negative 1 to the n plus 1 all over 2 to the n plus 1. Okay. Maybe you've seen things like 2 to the x. That's no big deal. Exponential expressions. This guy up top is probably a little different. It's negative 1 to the n plus 1. And it just is a mechanism for getting every other guy to be negative. Okay, so for example, a sub 1 will be negative 1 to the 1 plus 1, which is 2, all over 2 to the 1, which is 2 plus 1. So this first term, negative to an even power, will be positive, 3. And then the next term, because you're raising it to an odd power, negative 1 to an odd power, it'll be negative. Okay, so you get negative 1 all over 2 squared is 4 plus 1 is 5. And then the next guy will end up being positive. Okay, so it'll have a result, an effect of giving alternating signs to each term of the sequence. Okay. So they'll come in 2 flavors, basically, and sometimes you have to make these formulas up. Okay, so that can be a challenge. Let me get this rotated correctly. Oh boy. Okay, so that's good enough. So you can have the negative 1 to the n plus 1, but you can also have this other guy, a sub n equals negative 1 to the n. And the dealio is, if you see this negative 1 to the n plus 1, it's going to cause the even terms to be negative. So down here you can see a sub 2, the even guy is negative, whereas the odd ones will be positive. Okay? So this causes negative even terms. Sorry, negative odd terms. Oh, jeez. Negative odds. And this causes the evens to be odd. The evens to be odd. So negative even. Oh, wait, it should be the other way around. Not going good this morning. So this guy causes, it's exactly like this. So it causes the even to be negative. Even is negative. And then, so this must be the odd is negative. Okay, sorry about that. Okay. You may have noticed as you went through this problem that you could get the next number just by multiplying the previous number by 1/3. So if I multiply 1/9 by 1/3, I get 1/27. Of course, you have to tack on a negative. And then if I get to this guy, I would have to multiply by 1/3 again. So 1/27 times 1/3 is 181. Okay, so whenever you think in that way about the previous term being the basis for the next term, it's called a recursive formula. And that'll be what we look at here in the next section. Section 2, the recursive formula. And here, typically the general formula, like we were doing with before, won't be given. Okay? So let's look at the book. They want you to write the first 4 terms. They tell you the first term is 5, and then they give you a recursive formula, which is based off of the previous term in this case. And they want you to use that formula for any n value greater than or equal to 2. Okay. So we can list the first 4 terms. A sub 1 is just 5, and that's from the given information. So if you read the book, all of this is given. Okay. Then to get a sub 2, what you're going to do is use this formula here. It's for all n greater than or equal to 2. We're at 2, so we can use this. So a sub 2 is equal to 3. A sub n minus 1, so 2 minus 1. I'm nuts with the camera again. Sorry. Sometimes things drive me nuts. Sorry about that. Okay, so we want to use this formula to get to the next term. So 3a sub 3a sub 2 minus 1 and then minus 1. So this is 3a sub 2 minus 1 is 1 and then minus 1. Okay, and then a sub 1 is 5. So you're just going to plop a sub 1 into there. And now you have 3 times 5 minus 1 equals 15 minus 1, which is 14, of course. Okay. So a sub 3, you'll have 3a sub 3 minus 1. In other words, 3a sub 2. So you're just taking the previous a value. minus 1 equals 3 times a sub 2 is 14 minus 1. So, 14 times 3, I'll carry the 1. It's 42 minus 1, which is, of course, 41, and so on. Okay, so recursive formulas, if you ever heard of the Fibonacci sequence, that's the kind of recursive formula. So the Fibonacci sequence will go 1, comma 1, and then the next term is based off of these two, adding these two terms together. So it's 2, and then 1 plus 2 is 3, and then 3 plus 2 is 5, and then 5 plus 3 is 8. Okay. Okay, anyways, factorial notation. So we're getting a lot of definitions here. And it's basically just notation to help you do further math later on if you kept taking math. But I mean, everybody should have seen factorial notation at least once. So here we go. How does it work? It's just a way of writing something like 5 times 4 times 3 times 2 times 1. Okay? So instead of writing out that, you're going to write 5 and then put an exclamation mark there. So 5, it's read 5 factorial is equal to 5 times 4 times 3 times 2 times 1. So for example, I don't know, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So it has a recursive flavor to it because you can write 6 factorial as 6 times the previous factorial, which of course is 6 times 5 times 4 times 3 times 2 times 1. Okay. Some trivial factorials which are just given as definitions. 1 factorial is just 1, and then it's, you may wonder, what the heck is 0 factorial? Well, we'll define it to be 1. If you're interested in why, the number file people do a really good job of explaining that, so I'll just reference you to those guys, and you can watch their videos. What else? Oh yeah, in general then, n factorial, you can think of recursively as n times n minus 1 factorial. So just like out there with the 6 factorial is 6 times 1 less than 6 factorial. That's what that says. You could also then think of this as just brute force, writing out n times n minus 1 times n minus 2, all the way down to it always ends in 3 times 2 times 1. So that's how we write it. N times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. Okay. So the book is going to, run you through the gauntlet here and have you explore the notation. Let's take a look at number 20. So again, we have a sequence kind of problem. They want you to write out the first 4 terms, and we have some factorials to worry about here. Okay, so a sub 1 is going to be 1 plus 1 factorial all over 1 squared. So 1 plus 1 is 2, of course. All over 1 squared is 1. And then 2 factorial is just 2 times 1, so that'll be 2. Let's look at a sub 2. So a sub 2 will be 2 plus 1 factorial, in other words 3 factorial, all over 2 squared. 3 factorial is 3 times 2 times 1. 2 squared is 4. 3 times 2 times 1 is 6, all over 4. And of course, that's just 3 halves. Let's look at a sub 3. 3 plus 1 is 4 factorial, all over 3 squared. So we have 4 times 3 times 2 times 1 all over 9. We can simplify a little. So 3 over 9 is the same as 1 over 3. So I have 4 times 2 is 8 all over 3. Okay. Etc. Let's look at 24, see what that's about. We have 18 factorial all over 16 factorial. You can do brute force and literally write it out, and it's kind of insane, but you can do that. It's 18 times 17 times 16 times 15 times, etc. But hopefully you see that 18 times 17 times 16 times 15 times 3 times 2 times 1. The 16 factorial lives inside of 18 factorial. So you see, this is 16 factorial from right here all the way down. So you can essentially cancel those two out, and you're just left with 18 times 17, which is 306. So those aren't so bad. If you get stuck, you can always brute force it. But 28, you have to be able to work with this new notation, or you're just not going to be able to get it. Okay. So we have to go back to those general definitions for the factorial. 2n plus 1 factorial, what is that? Well, it's 2n plus 1. And then you subtract 1 away from that and put it right here. So the next term will be 2n plus 1 minus 1. I'm not able to zoom in, but 2n plus 1 minus 1 is just 2n. Okay. And then I can continue on that process. So 2n, for the next one, I have to go minus 1. So literally just then 2n minus 1. And then 2n minus 1 minus 1, which is 2n minus 2. And you continue that all the way down to 3 times 2 times 1. In the denominator, you have 2n, and then 2n minus 1, and then 2n minus 2, and then all the way down to 3 times 2 times 1. And then hopefully you see, there's a common portion which can be gotten rid of, so that from 2n all the way down is in common with the denominator there. So at the end of the day, you're just left with this 2n plus 1. Okay. Let's see what else we have today. Okay, the summation notation is a shorthand way of adding up a large number of things. Like instead of writing 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9, they decided they would use this notation to make life a little easier. So this is section 4, summation notation. Okay, so what the heck is going on? Well, let's say you had to write out 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. Okay? And you have to do it a lot. Like maybe you work at a bank and for some weird reason they have you write this expression out. Is there a shorthand way of doing it? And yes, there is. What you're going to do is write this funny looking E. It's a capital sigma. Okay? And down below, you're going to put what's called the lower limit. It's basically your starting place. So we'll say we want to start at 1. And then we'll put a formula in here to produce 1, then 2, then 3, then 4. And we'll go all the way up to 10. And this object here, this symbol, is actually the same as this thing right here. Okay? Let's look at another example. This is just an example. So another example, let's say, let's go in the other direction now. So the sum of I plus 1. Okay? And I want to go from I equals 1 to 3. So how do I do that? Well, you plug 1 into this formula first, so you'll have 1 plus 1. Okay? And then you increment I. So you add 1 to I, and you have I equals 2, and then you pop it into this formula, and you always put a plus sign in between all your terms. Okay, so this was from the first term. When I put 1 into here, I got 1 plus 1. Now I want to put 2 into here, and I get 2 plus 1. And then I want to put 3 into there, and I get 3 plus 1. Okay. So in the end, I'll have 2 plus 3 plus 4, which of course is 9. Sorry, I want to get my stupid camera back in position so I don't have to worry so much. On there. Jeez. Sorry. Seems like it's so easy, but that's good enough. Okay. All right. So let's get the general definition, and then we'll go ahead and look at problems from the book. So the general definition, you'll have the summation symbol, and then you have what's called a lower limit, and I is called the index, but the lower limit is this number 1, and then you go all the way up to the upper limit, which we're going to call n, and then you have a formula that tells you what to put each time. Okay? So when I put 1 in there, I'll have a of 1 or a sub 1, and then it's a summation, so you're adding all these things together. So it's like it's basically like a sequence, except you put an addition symbol in between the terms. Right? So a sub 1 plus a sub 2 plus a sub 3 plus dot 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 plus the one before n minus the one before n is n minus 1, and then finally a sub n. Right? So again, I is your index. 1 is the lower limit, and n is your upper limit. Okay, so let's go back to the exercises in the book now, and they want you to expand the sum and probably add it as well. So I equals 1 to 5 of the formula I cubed. Okay, so you start with the lower limit, and then you increment up to 5. So you should have 1, 2, 3, 4, and then 5 terms. So we go 1 cubed, so you just plug 1 into this formula, and then you plug 2 into the formula, and then 3, and then 4, and then 5. Right? And then we could add all that up. And I got 225. Okay. Let's look at another 38. The lower limit doesn't have to start at 1. Okay, it can start at 0. It can start at 3, making this problem. Let's look at this guy. So this time the formula is just 12. Okay, it's like the equation of a line. For any I value, the output is going to be just 12. So you'll have 12 when I is 3. You'll have 12 when I is 4. You'll have 12 when I is 5, 6, 7. Okay. So at the end, this is just 7, or how many are there? 5 12s. 5 times 12, which is 60. Let's got a more complicated one. I going from 0 to 4. And we have -1 to the I plus 1 all over I plus 1 factorial. Right. So this -1 to the I plus 1 gives you those alternating signs, right? And when it's I plus 1, it's going to be negative on the even terms. Let's go ahead and do these. So first, the lower limit says plug in 0 first. So -1 to the 0 plus 1 is just 1. And then I have 0 plus 1 factorial, which is 1 factorial. And then plus -1 to the 1 plus 1 is 2, all over 2 factorial. And after a while, you kind of see a pattern. Right? Be careful, though, if you're using a pattern that you recognize you're not stopping at this term. Right? This is I plus 1, so it's actually, if you were to list them out, this is I is 0, I is 1, I is 2, I is 3, and we hadn't reached the upper limit yet. So we need to go one more to -1 to the 5th all over 5 factorial. Okay? And then we could simplify it. Three factorial is 3 times 2 times 1. And if you find a common denominator and all that jazz, you'll get -19/30ths. Okay, you want to be good at going back and forth, so you want to be good at what they call collapsing and expanding. So right now we've been expanding. We also want to get good at collapsing these things. So for instance, 44, we have 1 to the 4th plus 2 to the 4th plus 3 to the 4th plus plus 12 to the 4th. And then they want you to write it in summation notation. So it's non-unique unless they tell you where to start. So in particular, the book will help you and say start with your lower limit being I equal 1. Okay? So in your summation formula, you'll have I equals 1, and then go all the way up to whatever. So the formula, it looks like it's going to be 1, 2, so it looks like it's just going to be I, and then they're raising it to the 4th power every time. And it looks like they're going all the way up to 12. And if you're not sure, what you do is just re-expand it and see if you get the same thing. You know, so if I were to re-expand it, it would start at 1 to the 4th, and then go to 2 to the 4th, and sure enough, it's mirroring what we have, okay, all the way up to 12 to the 4th, and yeah, that's what it is. Okay. Let's look at some other ones. Just 2 other ones, and we'll call it quits. So 1/3 plus 2/4 plus 3/5 plus plus 16 all over 16 plus 2. Okay. So again, you want to start your lower limit at 1. It looks like we're going all the way up to 16, maybe. Let's get the formula first. So it'll be apparently I all over, yeah, I plus 2. So it's going, yeah, it's going to go all the way up to 16. And again, if you're not sure, then just expand it, re-expand it, and see if it works. Let's do one more, 54. This is kind of a famous one, and it's foreshadowing what we're going to be doing here in the next sections. So it's called a geometric series, or sorry, a geometric sum. So series will come later in calculus. A plus AR squared plus dot 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 plus AR to the n minus 1. Okay. It's a little harder one. Starting at A equals 1, it seems like I always have an A in there, and then R to something that's changing. So the first one would be R to the 0. It's not there, but R to the 0 would be 1, and then R to the 1 would be here, R to the 2. So R to the I minus 1, I think we'll flip the bill, and we'll go all the way up to then n. That will give me AR to the n minus 1. Okay. So hopefully we'll see those in 10.3. We'll look at the geometric sequence as well as, I guess we will look at series in this class. Okay. Okay.